Simplex Pachinko, and there we go. Audio sort of fixed. That feels like it's not in the same place. Alright, let's check here. Maxing out around 50, give or take. And my audio is not... Huh. Yep. Sorry, my microphone is not in the same place it was earlier. And that's slightly distracting. Check, 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 check. That maybe feels a little bit better. We will see how that goes. Hope everybody's having a good night. We are talking about calculus and the very impetus of... Thank you, for me. We're talking about the impetus of calculus and how exactly it got started, at least mostly. P. Vermi. Alright, thank you. I couldn't be sure because I also got a, not that one. I ended up getting a P.G. Woodhouse book recently. Oh. Actually, is it this one? Yeah, it is. Oh no, you know what? It isn't this one. Anyway, yeah, it wasn't Jeeves and Wooster. It was the other one. I can't remember exactly, but there is a character in it whose name is P. Smith, but it's not like P. Smith, like P with an S and then M-I-T-H. It's like P and then Smith is all lowercase. So, Smith? Question mark? I didn't realize that that was actually the place where that character's name came from, because the one and only Phil Foglio adopted that name as part of his Buck Godot Buck Godot Zap Gun for Hire series. So actually, that one's all sorts of messed up because it's got like capitals in all the wrong places. That one is a very odd story. And all the other stuff I should have done earlier. Get my tools. Okay. So we were talking about the nature of limits and sequences specifically, and this also involved back up here we were talking about how exactly do we get limits. So here we were talking about convergent limits, which will converge to a limit we call L, when for any very small number, and in fact it doesn't have to be a small number, but we like to think of it as a small number, that is bigger than 0, there exists some n such that for such that the distance between a sub I, wherever a sub I is, and L, our limit, is going to be less than that particular epsilon for every single term after that particular I value, which we call, again, n. So we said here, after some particular value, we're going to say that this is going to be over that L minus epsilon. We're going to be a certain, less than that certain distance away for every single term after that line. We're not quite there yet. Okay. I came back and like this was, it's also tilted, you can see slightly. Like that's parallel with the curtain, and that's not parallel with the top of the screen. It really should be. It's not going to bother me, I promise. Right, we had finished the chapter 1 review, which was all the pre-calculus stuff. We talked about monotonic bounded sequences. When it's monotonic and bounded, that means it's convergent. And sequences and their limits behave as linear operators. So here, if we do, right, the limit as I goes to infinity of a sub I is called capital A, and limit as I goes to infinity of b sub I is going to be capital B. Then we end up with the limit as I goes to infinity of a sub I plus or minus b sub I, so the sum or difference of two sequences. They all get added point-wise, essentially. So the first terms get added together, the second terms get added together, etc. Then that's going to get you the same thing as their individual limits, summed or differenced, whatever you want to call it. And limit as I goes to infinity of k times a sub I, where k is a constant, is going to get us k times capital A. And same thing happens for product and difference, interestingly enough, because these are point-wise multiplications and divisions, where we're just taking our first terms and finding their product or quotient, second terms, product or quotient, etc. And in that case, we end up with the same product of AB and quotient of A over B, provided that, again, no particular B sub I is going to be 0, and our limit B is not going to be 0 either. Otherwise, we can have problems. Naturally, right, when you divide stuff. Our squeeze theorem we talked about. So if you have an upper sequence and a lower sequence, and both of them end up going toward the same value, going toward the same limit, then it'll turn out that any particular sequence that is always between those values is going to have the exact same limit, right? Because it has to stay between the other two, and if the other two converge, then the one in the middle is going to have to converge with them. Right, we said that it only really has to be between them for, from a certain value on. It doesn't have to be there every single term, just as long as you know it's going to be there from this particular point on. Correspondence theorem was something that, it's a name that I made up, but means the same thing. You've probably heard it before. For all x equals I, if we have f of x is equal to a sub I, then the limit as x approaches infinity of f of x is going to be L, if and only if the limit as I goes to infinity of a sub I is equal to L. Right, so we're always going to get x and I are the same thing. One is continuous and one is discrete. Right, so our f of x is going to be a continuous function. A sub I is going to be a discrete sequence. Then it is perfectly acceptable to say, like, hey, these are going to be the same thing. Okay. All right, so Ivan Neo, good evening and welcome. Let's see. We got examples that exist in, right. So anybody who hasn't been here, we're doing cracking the GRE math test. So this is the math subject test of the graduate record exam. So if anybody is going to apply for postgraduate, master's degrees, PhDs, etc., you need to usually take the GRE. And if it's in a STEM field, generally you need to take the math subject exam. So it could be interesting. There were definitely some things that I did not know in here because I did not take those particular classes. So topology for one. So by the time we get there, right, we're probably gonna. This is an interesting project. I don't know how long it's gonna last, but we'll see. And if anybody has any particular questions that you'd like to ask that are not related to GRE, that's perfectly acceptable too. We'll, take a little bit of a break and go do some other problems. So feel free and ask. You can do that here, or you can do that in Penn Center's Discord server, which of course I closed Discord. It eats so much resources, it's kind of ridiculous. Okay, copy that. There's that one. So that is for Penn Center, who is one of our fellow math streamers. We've got a whole bunch of them. If you go into that Discord server, that is called The Elements, after Euclid's famous work. And we have individual streamers. He separated us out. Okay, cool. So we have separate streamers. Dr. Gold at Actual Education. Me, Obi, at Insimplex Pachinko. Hey, Georgia. Thank you so much. We have Penn Center, E.N. Stuckey, Zach, at E to the 2i Pi. What on earth is that? Oh, that's just the ending. That's weird. My screen's slightly distorting something, and I thought it was extra characters that were fading into a black zone, at the end of a statement or something like that. No. And then we have other educational streamers. Rende Zero. It looks like Rendeo, but the last one's a 0. Talos Teaches, Xiphon SVC, Math Spellbook, and Phobos Dream are the ones who are currently attached and said, I would like a space in the server. There's a bunch of other people. Got here via TKF. Awesome. So yes, TKF, the Knowledge Fellowship, is also another group of really awesome people. Nope, not that one. So, TKF is the Knowledge Fellowship. Awesome group of people. There are pretty much any subject that you would like to look up and learn something about. There is somebody out there who does it on Twitch, or maybe YouTube, but nonetheless. They are linked through TKF, and everybody there has met, spoken with, done some sort of... There's been some sort of vetting process. where they've like watched our stuff and made sure that we're reasonable. With the understanding and big asterisk that if you ever screw up real bad, they have the right to kick you out. In addition to those awesome people, we also have Moohoodles, Science streams. Dawn Factorial is currently on. Danny Highway is generally somebody who has been around. He's currently taking a bit of a hiatus. So, anyway, Volcano Doc. We got a few more, but we will, yeah, we'll get back to doing some math here. But yeah, if there's any particular subject you want to know about, like, TKF is a good place to go to find somebody, or get recommendations if there isn't anyone there. Example A. This says what we want to do, right? Our actual objective is to determine it does not even determine whether. So we need to show that each of the following sequences are convergent. So as we said above, in order to show convergence, you need to show that the sequence is bounded, and the sequence is... I just literally said it, like, bounded and monotonic. So it will continue to increase or continue to decrease, potentially having the exact same value for a while. That's perfectly fine too. But then eventually we start shrinking in toward toward a particular value. And then we try to figure out what that value is. So for A sub I is going to be equal to that's a fraction. 4 I cubed minus I squared plus 5I all over 2I cubed plus 6I squared minus 11. Right, so in order to find out whether this thing is convergent, again, like we said, we need to show it is monotonic, so after a certain point it will just continue to either increase or decrease. And to show it's bounded. It's actually a good question. I haven't done that in a while. One thing that we can do... Well, there's a few options. So, one thing that we can do is to literally just divide. So we can go in here and divide... do polynomial long division. And it's going to be a little bit challenging because there's only like one term that we can really do. But it is possible. The other option is to take this and say, We can multiply both the top and bottom by I to the negative third, which will eliminate the terms in our first terms, both top and bottom, and then in the second and third terms, it's going to make a fractional value. So here, a sub I is going to be equal to, this doesn't actually change the overall value of anything. We just say that this is going to be 4, right? 4 I to the third times I to the negative third. Those two I terms end up becoming I to the 0 when you multiply them, minus I squared times I to the negative third is I to the negative first, so that's 1 over I. Okay, plus, this is going to be 5 over, and then I to the first times I to the negative third is I to the negative second, so I squared on the bottom. That is the numerator. And then the denominator, same basic idea happens. 2 times I to the third times I to the negative third is just going to be 2. Second term is going to be 6 over, again, same thing, I. And third term minus 11 over I cubed. Okay, and then we reason through this. So there are several different ways to like issue a proof as far as what's going to happen. So we could say, let's take the limit as I goes to infinity. I don't really actually like using I prefer K most of the time. Of a sub I is going to be equal to limit as I goes to infinity of the above. Okay, so we could discuss that in just a second. Let's try and figure out if there's a nice way to do this. So if we discuss what's happening here, we say like as I increases, all terms with I in the denominator become smaller in value. The numerator will become closer to 4. The denominator will become closer to 2. Alright, that's going to be the same for both of these things. The value of 5 over I squared may in fact be slightly larger than 1 over I for some amount of time. But we can always say that like as our I keeps increasing, we're going to notice that those particular effects become overall smaller compared to the 4 and the 2 that are just sitting out front. So we end up with something that is going to become closer and closer and closer to 4 over 2. So let's actually check it out. So 4 minus 1 over x plus 5 over x squared. Yep. And then 2 plus 6 over x minus 11 over x cubed. Because we're trying to show that that actually works. So when you get into some particular interesting. Yeah, there we go. Bingo. When we get into above calculus, so we're talking like real analysis, which is usually a senior level math majors class. And P. Verme, I don't know where you are in your journey, but may well have already taken it. But in terms of like real analysis, then you start talking about like where do all of these shortcuts that we've kind of developed through our algebra, trig, and calculus classes, like where do these shortcuts really come from? How do we prove that they're actually real, that they always work, or that we need certain conditions? Many years removed from calc. Yep. Multivar. Okay. Nice. Yep. Okay. So you didn't take real analysis then, but stats is, yeah. That was a fun set. I was not the best. I think there was too much data science and practical application for what I wanted, but that's a me problem. Okay. So our numerator, yeah. And Zach, e to the 2i pi, is very much a data science person, so you probably want to check him out. Yeah, I got mine yesterday. They missed a couple of spots back here. I gotta go trim that later. So go check out Zach at some point. Anybody who hasn't, he's definitely worth a watch. And we like absolutely we have converged on a very similar teaching style, which mostly involves something similar to, although legally distinct from, Peter Liljedahl's Building Thinking Classrooms. So if anybody's interested in math education, we can discuss this sometime. Definitely worth a read. If you have a library or something like that that has it, definitely go for it. It is a mite bit expensive otherwise, but So here with this one, we see that this reaches a minimum at about 10, or at 10. And then after 3.95, it starts going back up again, pretty close to 4. I think 4 might be our... Oh, right, yes, obviously. 4 is the convergent value. We already discussed that. And then here we have a maximum at 3.7 at an x value of 2.34. This being a sequence, right, it is actually going to reach its peak at 2, comma 3.625, and then at 3, we end up with this number, 3.59, so it's lower than the other one. So we get those two values, and then after that point, this is going to decrease continually until we reach 2, or close to 2. Absolutely. Instructional techniques. So at some point, I had also arbitrarily decided that like Monday was going to be reserved for kind of the more educational side of stuff, and Wednesday was going to be reserved for more like doing problems, things like that. I'm not doing that right now, but like if there's a... I would say if you have a preference, like Monday or Wednesday, then we can definitely do that. Normally I start at 9 o'clock BST, so it is 2000 hours UTC. Yeah, we're just using continuous for illustration purposes. And I mean, in theory, like I could drop that out and say I only want integers. Right, I think we can... So like if I went with like 2, 3, 7, and then I went with like y1 is equal to 2x1. No, doesn't like that. Okay, it's worth a shot. Equations not allowed. Okay, fine. There's got to be some way to do that. Anyway, not important. Or like... No. Doesn't know what I'm talking about. Alright, that's fine. Nope. Don't know what I'm doing. It's fine. So yeah, point being, numerator becomes closer to 4. And here we said that, thank you P Vermi for the follow, n for this one is going to be equal to 3.5. Nope, and it's going to be 10. And for the lower n is going to be, I think it was going to be 3.5, so, or 2.6 or whatever it was. 2.34, and 10. So those are going to be our two x values where it will start becoming closer to those particular values and closer and closer and closer forever from those points. Technically, capital N can be 9 because 10 is in the middle of that pattern, or I want to say middle. Right, for all I greater than n. So here, because this is strictly greater, then we're allowed to say that that n is going to be 9 for this one, because at 10, we're going to have everything raising up from that. Okay. So for this, we're showing that these are going to be monotonic for all, or for all I, such that n equals 9. Right, we basically are taking an intersection here, figure out, okay, n is 2 means everything greater than 2, n is 9 means everything's greater than 9, intersect the two, it's everything greater than 9. So our capital N value is going to be 9, where the entire fraction is going to be monotonic. Technically. Right, let's just make sure. We'll do this one as f of x equals this. And we'll do this one as g of x equals this. And then what we want is to do h of x is equal to f of x over g of x. It's not even. Right, this one's actually monotonic even where n is greater, or n is 2. So we get values greater than 2.9 are going to be just forever increasing. I'm trying to think if maybe this is a better, like, blind way to do it, where you're just going to say, oh, look, it's just going to be the intersection of these two, and we'll deal with it. We'll deal with any, like, deviations from that by actually doing the whole thing later. Right. Megalomorph. Horrible idea. Dating sim that mostly takes place in a study group for a math class. Oh no. Calculust. Just trying to think of a calculus pun for talking about your dating pool, but that's probably more of a discrete structures joke. Set theory. Okay, so when you graph it, it's monotonic for all I greater than 2. And then we have to show that this is bounded. So again, again, numerator and denominator getting closer to 4 and closer to 2 with these particular n values, 9 and 2. This is going to tell us that, okay, 4, or the numerator, increases, and denominator decreases to 2. Again, n equals 9, n equals 2. No, don't do that. Look, as much as I like that Miles Smith song, that would be a big no-no from Twitch. So, Academy of Useless Ideas, good evening and welcome everybody. My name is Obi-Wan Pez, this is N Simplex Pachinko, and we're doing some math tonight. We're trying to crack the GRE math test. So this is the subject test for mathematics. If anyone is intending on being a graduate student, you probably have to take this within the STEM field. You probably have to take this, so we're mostly looking at it just as like some interesting, what are some interesting problems that we can work on. And also, as we get through each of the sections, I am essentially teaching the main idea of each of the group's problems as we go through. So far, we have only done pre-calculus, which was long enough, to be fair. Tonight is night 12, and we started on calculus last night, or no, sorry, Monday night, when we talked about sequences and dealing with limits of sequences. Right now, we're trying to do a couple of examples. We're trying to do a couple of examples and figure out how to best describe, finding how each of these sequences are convergent, and in doing so we have to find out that they are monotonic and that they are bounded. So for all I greater than some particular value, we either need a sub I to be greater than or equal to a sub I plus 1, or less than or equal to a sub I plus 1. And to show that it's bounded, all convergent sequences have some m such that absolute value of a sub I is less than or equal to that particular value. Or, again, greater than or equal to that particular value. So here, we've shown that this particular ratio ends up being monotonic from a blind point of view where we did not see what was going to happen. Like, I hadn't graphed it yet. I said let n be 9 because n was going to be 9 for the numerator and 2 for the denominator. And let's just take the intersection of those two values. N equals 9 is going to be our, like, least inclusive in this particular setup. But when we graphed it, turns out it's monotonic when n is 2, and like any value bigger than that, it's still going to be monotonic. So that's kind of nice. I was kind of curious as to whether and Megalomorph might know, whether this example here will always be more inclusive than a blind intersection of their two monotonic quote-unquote domains. Maxie, how's it going? Good evening and welcome. Yep, that's fair. We are trying to show that this sequence here is going to be convergent. I've also contemplated switching from I to K because, quite frankly, I don't want to do all those dots. So everybody coming in from Academy of Useless Ideas, thank you so much. Everybody who has not yet met them, woo. I can go check them out there. So, my reasoning on this one is that as our numerator begins to increase after n equals 9, and the denominator is decreasing, both of these things are increasing the value of the ratio. Now, as we discussed up above, as we discussed above, numerator is going to increase to 4, and, right, this is where it gets interesting. Right, let's bring both of these ideas together. Let's not make that J. Oy. So the numerator is going to increase to 4, the denominator is going to increase to 2. We know from experience at this point that, yeah, as I gets off to infinity, all of these other values are going to get close enough to 0 that they're just not going to matter. So, eventually, right, L is going to be 4 over 2 or just 2. So we could say, like, let M be equal to 2 and all A sub I, absolute value, are going to be less than or equal to 2. So we know that it's going to be bounded. We could also say that this is going to have a bounded value from what? Right, so from 3, we know that lower bound M is going to be greater than or equal to 1. Right, we could just make up some arbitrary value, which is lower than this. or we could say it's greater than or equal to that value, 1.17526, etc. Right, at 2, this is 1.3, that's too high, so we go out to the next number, right? Keep in mind again, this function h is actually going to be a discrete sequence rather than a continuous function. This is for illustrative purposes. Hey, famished. Yeah, we're doing all right. Apart from the cough, but you know. Hay fever. Lovely season. Right, we could also let m lower be equal to, again, 1.1. And so m, no, a sub I absolute value must be greater than or equal to 1.1, provided that, again, we have a particular number n, right, for all I greater than, what did I say, 2. Yeah. Yeah. So the interesting thing with me is that every time that I went back to school and every time that we ended school, I ended up getting this massive allergic conjunctivitis in my right eye only. It would just turn this, you know, bloodshot, pinky red, and everybody be like, "Ugh, why are you here? You should be home. I don't want to be, you know, you should take that somewhere else and not be contagious." And I'm like, I'm not contagious. Like, you could literally touch my eye, put it in your eye, and nothing would happen. It'd be a little gross, but... Okay, so here... we could call that M sub upper. Yeah, every single semester, like start and end, it would just... And I think that it was maybe due to increased use of the whiteboard pens and like just rubbing it off the board would like get dust in my eye. It was much worse when I had chalk. And Zach can fight me on this, right? Like, I will agree that chalk is much better for that really mathy feel. Okay. So we have bounded and monotonic for all I greater than, realistically, right, like greater than 9. We said that a lot of these have an I that is 2. And so we could probably even say that if we wanted to go with it, but, you know, just to be on the safe side, we could say here I is going to be greater than 9. So a sub I equals that stuff up there. That one. Converges. So I will admit, right, this was the long way to do it. We were just kind of proving that it works and using the best and most rigorous type of proof method here. No. By just basically working through a bunch of arguments and then graphing it to double check that our arguments hold. It's bounded, it's monotonic, therefore it converges. Okay, so coming back up here, numerically, we could also just do this, right? We could take this thing and say, what happens if we just take the limit? Right, so the limit as I goes to infinity of a sub I is going to be equal to, here we end up with a 4. This is going to be minus 1 over infinity, right, is just going to be 0, plus 5 over infinity squared is also 0. Right, we got a 2 here, plus 6 over infinity is 0, minus 11 over infinity is 0. So we end up with this particular limit as I goes to infinity of a sub I is equal to 4 over 2, which is 2. So we've shown here, right, this is the real shortcut, the like fast way of doing limits, is there some way that we can show as I goes off to infinity that the rest of our sequence can be broken down into nice parts that infinity can deal with. In theory, right, later on we'll look at some that have like infinity plus infinity, infinity minus infinity, infinity over infinity, infinity times 0, right? Things that are what we consider indeterminate. So we can't figure out exactly what's happening because depending on the individual particular behaviors, you could end up with those particular things having any of the behaviors that we've looked at. So is it going to 0? Is it going to infinity? Is it approaching a specific value? We don't know. So we have to go through certain tests to be able to figure out, is this going to converge or diverge based on our algebra? Okay, so ads are about to start in like 2 minutes. So I think we'll probably jump it and say, like, I think we'll probably jump start it and just say, let's do it starting now. I will put up number 2 for everybody to look at. I don't know, B. Right. B says A sub K, let's do K, is equal to square root of K plus C, really screwed it up there, all right, minus square root of K, where C is a constant. All right, we'll actually put up C as well over here for anybody who wants to look at it. A sub K is equal to fraction 1 times 3 times 5 times dot 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 times 2k minus 1. Now we're not going to jump start it, it's just going to go by itself. Over 2 times 4 times 6 times dot 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 up to 2k. Alright, those are going to be our next 2 problems. Take a look at them, see if you can make any sense out of it, and then we'll be back in 3 minutes. Thanks for coming, everybody.
Upload your video to Spotify, turn views into fans, and monetize your passion.
Alright, welcome back. So, redeemed good form as we usually do. And we're going to do the Tai Chi form that we have finished this last week. So, generally speaking, we can do what's called the stepping version of this, where every time you do a move where it's appropriate, you step forward. I'm going to try to align myself with the camera this time. So, more or less, just kind of get loose again. What we were trying to do when we get loose is like use your knees, use your legs to effectively take your energy and put it entirely into your arms and the arm movement, and therefore you don't actually want to you don't want to like push that energy into your arms. What you should do, there we go. What you should do is basically let them go completely limp, and then as you swing like this, you're just giving it a little bit of emotion, and it puts all that energy, just like pushing a kid on the swing, puts that energy into your arms. We've been doing that with like one leg forward, one leg back, same deal, or use your hips slightly to differentiate between the two. Rock back and forth a little bit and make that happen. It's kind of like alpine skiing. And then you go the other way, or cross country skiing. There we go. So I'm not really putting any energy into making my arms move, with the exception of rocking back and forth on my feet. Alright, once you're warmed up, the way the our main moves are so we've done ward off, which is keeping the front hand out like this. This is trying to touch against somebody so that you can kind of feel their motion and their movement. If they ever try to like do something to move and shift around you, then you're going to feel that movement and then you can respond accordingly. The backhand keeps a structure. So this is a bit like ballroom dancing, right? If you're out like this, you keep this structure and then you hold your partner and you hold your partner's hand, and keeping that structure allows you to indicate to your partner where you're moving. In this particular case, this is actually just holding your muscles in a good position. So we have ward off, which generally comes out like this. Then we have, I remember the name of it now, it's roll back. So we come back this way, put our hands together, and then press is like this. It separates and then becomes push. So those are the four basic movements, right? Ward off, roll back, press, push. And then the four, those are the four cardinal directions. And then the four diagonal directions are, when we're going the other way, we had pluck, where you're taking the other person's hand, you're basically just grabbing them around the wrist and pulling them back toward you this way. So pluck, split, where you basically are using your momentum, carry it forward, and then allow that energy to go into your hand for either a straight up slap, which if you hit in the right spot, like because it's just slapping so many nerves, it can actually stun the other person. So got to be careful when you don't want to do it for real while you're in a class or something like that. But and again, this allows it to, if you hit your forearm, this allows your hand to get some extra energy by whipping. And you can also do that as a ridge hand, but my instructor much prefers a just straight up slap. So split, pluck, split, and then there's an elbow. So we come back, oh, right, we grab somebody's hand, for instance, if they have grabbed our wrist, you disconnect yourself from them and shift your weight backward and then lean forward into an elbow smash. So that is one movement. We go from the end of split. The one movement for elbow is to disconnect and return. Right? And then we also have a movement for shoulder, which is the fourth diagonal on our chart, which is to step back. We keep our left hand up as a guard, step back, and then come forward and throw the elbow or throw the shoulder in. And then at that point, it also might allow your hand to whip forward. And if that's in the right position, you've just done a bag tag. Oh, it's so awful. All right. So the actual form puts all 8 of those moves together. So we start with inhalation. Press fingers. Come back. Exhalation. And then we move left. This is kind of the stereotypical Tai Chi thing. We hold a ball of energy. And then we come back to the right with a ward off. At this point, I am pressing into the ground, forward on my front foot, backward on my back foot. And this kind of like forces me into the ground and not able to move very far. We go a little bit further. Keep this hand out. Move this hand back to about our elbow. And then move left into a rollback, press, roll back, or put weight on the back foot, and then we go into a push. So that's going to come back and onto our front foot, and then we come back to our back foot, pluck. I shouldn't go that far. Kind of keep both legs more or less on the ground, pluck, and then split. Right, then go into elbow, and then go into shoulder. And then from here, we can do a ward off again. And now we're back here, so we can just cycle through the entire form. We start with, right, ward off, roll back, press, push, split, nope, pluck, split, elbow, shoulder, ward off, roll back, press, push, pluck, split, elbow, and shoulder. Ward off, roll back, press, split, elbow, shoulder. We just keep repeating that until we get all the way across the room. So that's your Tai Chi lesson for the day. All right. So then we want to do the same more or less thing here, where we want to look at this and say, if we started with the one on the left, right, how can we prove that this is going to end up being convergent? Again, we would want to show that this is bounded, and we want to show it is monotonically increasing. So, hang on. Not really my thing. Okay, so we have a similar problem if we attempt to just look at this in terms of, plug in infinity in for k, right? Find the limit as k goes to infinity. Here we end up with a square root of an infinite number minus a square root of an infinite number. Okay, well, it's only off by a shift of c, so, like, that's not going to help much. Right, we do know that x plus c is going to be greater than, x. We do know that k plus c will be strictly greater than k. I guess that wasn't established. Yeah, that wasn't actually established. Right, and it doesn't actually matter, because right, so c needs to be greater than or equal to k, right, for all k. Otherwise, we have a domain issue. Nope, sorry. Less than. Whatever. We'll just put it the right way around. K plus c is greater than or equal to 0, right, for all possible k. K is, generally speaking, going to be from 1 on up to infinity, but I don't know that it specifically says. Okay, they start with a sub 1. We've also been known to start with a sub 0 before. It's perfectly fine. You just have to define it ahead of time. So, define whether we start with a sub 0 or a sub 1 beforehand to make sure that you understand, like, what's actually going on here. So, for this stuff, we're going to start with a sub 1. Okay. So with this, yep, P-Vermy, thanks so much. We'll see you around, and, you know, let us know if you need anything. Want to see any particular examples, anything like that, and we'll catch you next time. We do Monday, Wednesday as math stuff, and Friday is game type stuff, and then, like, gaming type stuff whenever we feel like it otherwise, or if we have, like, a strong request for something mathematical, then we can do those on extra days as well. Yep, definitely. Right, so for all k being k is going to be greater than or equal to 1. Therefore, c is going to have to be greater than or equal to -1. Bossgans! Thank you so much for the follow. Actually, right, let's put that down. Put that down 1, because that comes after realizing that k must be greater than or equal to 1. Okay, so, I mean, in theory, we could do something like... We could, like... We could do induction for that. Be kind of a pain in the rear. But we don't need to. Okay, so we need to show that this is bounded. For all c greater than or equal to 0, then we end up with those two square roots, right? All a sub k must be greater than or equal to 0. And for c equaling -1, a sub k is going to be less than 0 strictly. So for this one, we have a lower bound. M low equals 0. And for this one, we have an upper bound. And upper is going to be equal to also 0. Now, here's the other thing, right? Is that the bound we actually want, though? Okay, yeah. So eventually, because we're subtracting these two things, eventually this is going to get closer and closer to 0, because the difference between the two square roots is going to become negligible. It is going to take a long time for that to happen, but that's the idea. Okay. So the next question is it monotonically... Is it monotonically increasing or decreasing according to all this good stuff? So as k gets big, right? As k goes to infinity, we see the radicans at approximately the same size and relatively approach each other's value. We find the difference between the square roots which becomes smaller in value. So these two values are continually approaching each other as we go further and further out as k gets bigger and bigger. So I would say yes, it turns out that for nope, c being greater than or equal to 0, a sub k is always going to be greater than or equal to the next value. And so therefore this is monotonically decreasing. With an asterisk on when c is equal to 0, we end up with the exact same thing, so it's always going to be equal to 0, which technically means it's monotone, just like my voice. For c being less, nope, c being exactly -1, right, a sub k is going to be less than or equal to a sub k plus 1. So this is monotonically increasing. still fits this definition. So, bounded and monotonic. It implies that this is convergent. Okay, algebraically. Because nobody's going to be happy with that. Alright, a sub k is equal to, this is k plus c minus square root of k. There we go. Okay, so how do we do this? Well, right now what we can do is treat this like a fraction. And then we can multiply both top and bottom by square root of k plus c plus square root of k. This is going to be our conjugate, rational conjugate, over 1. So, square root of k plus c plus the square root of k, both top and bottom, ends up getting us a sub k is equal to, the first term is going to be k plus c. We get a root k plus c times root k minus a root k times root k plus c, and those become 0. And then we get a negative root k times a positive root k, which is going to be a negative k, all divided by. The denominator is the square root of k plus c plus the square root of k. Okay, so that means that a sub k is going to be equal to c divided by square root of k plus c plus square root of k. And then we look at this and say, what happens when we take the limit as k goes to infinity of all of it, left and right side? It's probably better form to put it literally on both sides, but yeah, it's fine. Okay, so then we get here that a sub infinity, which is oftentimes our L, right? Our limit is going to be equal to c over. This is the square root of something infinite plus the square root of something infinite. So this is going to be c over infinity, which is 0. Right. Its square root of infinity is also infinity. So both of those are going to end up being just infinitely large. And therefore c divided by a constant c divided by 0. Nope. A constant c divided by infinity is going to be equal to 0. With the exception of if c is 0 itself, then we might have another problem. But for the most part, we're just going to deal with it. Oh, no, wait. If c is 0, then it's 0 over infinity, which is still 0. Never mind. We're good. L is always going to be 0 for this. Alright. And then somebody looked at part C here. So again, same deal. We want to find that it is bounded monotonic, and therefore it must be convergent. So This one's going to be a bit trickier. Okay, so we want n is going from, we're going to change that to k. It's going from 1 to infinity. No. Yeah, all right. This is totally going to work. 2k minus 1 over 2k. Nice. Alright, so it looks like it's going to 0. One would hope. Okay. We'll go like 1 to 100x. 0.01. 10,000x. 0.001. Ooh, interesting. It may stop at 0.001. So I don't actually know how to necessarily deal with that. Alright, this is the product of... Okay, so monotonic I think we can do because that's going to be, we've already seen it, right? It's just going to keep decreasing. So every time that we do this, we're saying that a sub k is going to be greater than or equal to a sub k plus 1 was what we saw. So let's just essentially double check it, right? This is going to be 1 times 3 times 5 times dot 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 times 2k minus 1 over 2 times 4 times 6 times dot 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 times 2k is greater than or equal to 1 times 3 times 5 times dot 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 times, this is going to be 2k. That can't be 2k. Okay, nope, 2k plus 1. Divided by 2 by 4 by 6 by dot 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 by, this is going to be 2k plus 2. Okay. So all of this stuff, right, there is also going to be, okay, let's go like this. There is also going to be these two terms, 2k minus 1 times 2k plus 1, are both going to be in there. Here, this is going to be 2k times 2k plus 2 is also going to be in there. Okay, now since this is all positive numbers, right, we can divide all this stuff with all this stuff. On the left, we get 1 is greater than or equal to 2k plus 1 over 2k plus 2. Or 2k plus 2 is greater than or equal to 2k plus 1. We know that this is true. If you want to be pedantic and go any further, then congratulations, you've been more pedantic than I would. So, it's going to be 2 greater than or equal to 1. So, yes. Alright, so that's an algebraic way to show that we have monotonicity. And then bounded. So as k becomes really, really big, we multiply by another 2k minus 1 over 2k term. Which is less than 1. Which makes a sub k smaller. So we can say that this is bounded by 0. Right, so a sub k equals 0 is going to be our like lower bound for all this. If we multiply by an infinite number of terms which are all less than 1, by definition, right, that number is just going to keep getting smaller and smaller and smaller. So at the, I wouldn't say worst, but if we were to say, yes, well, definitely an infinite number of numbers that are less than 1 are going to multiply to, you know, a very extremely small number, then you could argue that 0 can be the bound for it. In theory, it could be a different number. Like it could be 0.9 is the lower bound for this. But because we're continually multiplying by new numbers which are also smaller, then this is certainly going to be bounded, at the very least, by 0. So bounded and monotonic, therefore it's convergent. Again, we don't know what it's technically convergent to, but at the very least, we just know it is convergent. D. Alternating 1 over n squared. So a sub k is equal to negative 1 to the k over k squared. Yep. Okay, so 1 over k. K squared gets smaller. Therefore, we have boundedness. Right, 1 over k squared. Okay, even if we put the negative 1 to the k, we basically just say, okay, the absolute value of this thing must be less than or equal to 1. Alright, so we have a maximum value that this is going to be within, and then monotonicity, we say that in order to show monotonicity, okay, nope, you're doing it to me again. Don't play that advertisement. Hmm. Hmm. So, negative 1 to the n is not monotonic because it oscillates. Hmm. Okay, that's fair. Okay, so this is not monotonic. Since it oscillates. But we can go a different route instead. Let capital A sub k be equal to 1 over k squared. C sub k be negative 1 over k squared. So, C sub k is less than or equal to little a sub k is less than or equal to big A sub k. A little a sub k is equal to either of the other two oscillating, right? So it's going to be either one or the other. right, for all k. Technically, it's just greater than or equal to 1, so we'll let that go. Basically, this is going to involve the squeeze theorem. So we just say that, oh look, since we're going to use the squeeze theorem on this, little a sub k just needs to be between, meaning also potentially equal to, either of our other functions, right? The one that's on the negative side, the one that's on the positive side. And the limit as k goes to infinity of 1 over k squared is equal to the limit as k goes to infinity of negative 1 over k squared, which is namely 0. Therefore, a sub k, the limit as k goes to infinity of lowercase a sub k must be equal to 0 by squeeze theorem. Alright, this may not be entirely obvious, but that's alright. There is a rule for it in here which said, like, the k to a power will always, or 1 over k to a power converges for n greater than 1, or greater than, yeah. Right. This is going to be a sub k is equal to the cosine of n to the n, or k to the k, times e to the negative k. So, this is oscillatory. Cosine of x always has to be between -1 and +1. Therefore, we're going to use the same argument for squeeze theorem there. Capital A sub k is equal to let capital A sub k equal e to the negative k, and c sub k be equal to negative e to the negative k. Therefore, c sub k is going to be less than or equal to lowercase a sub k is less than or equal to uppercase a sub k for all k greater than or equal to 1. Again, by definition, and the limit as k goes to infinity of e to the negative k is equal to the limit as k goes to infinity of negative e to the negative k, which is equal to 0. So, therefore, once again, a sub k lowercase is going to be equal to cosine of k to the k times e to the negative k has a limit. K goes to infinity of 0. Alrighty. Anybody have any questions there? Let me know. Apart from that, I am going to be joining up on Elite Dangerous with the Distant Worlds 3. So this is a Elite Dangerous mission, question mark, which basically is taking a like science exploration type thing, and they're doing a little bit of an RPG, jumping people out to unknown areas, having everybody kind of explore everything around a certain area, and then bring the exploratory data back to the mothership. There were, I believe, thousands of people who had signed up before, so pretty awesome. So we will be signing up Obipez from Boop Brigade. Ooh, I misspelled it. Main role we are trying to get into is to be a scientist with optional as explorer and I believe fuel rat. Maybe logistics? I don't know what I want. Environmental officer. What? I don't remember that. Fleet support, scout. Yeah, okay. Anyway. So we will be sending out the Mandalay, which is the high exploration ship, and trying to get into this particular group. So I think it ought to be cool. It'll be an event type thing that we run for, I don't even know how long it will be, but it may end up being like weeks upon weeks, in which case I may or may not end up using it at all as stream fodder. So we'll determine what's going to happen. I'll probably be on there on like practically a nightly basis unless I'm streaming here. We're going to go and head over to Dr. Gold at Actual Education and go hang out at his. He's doing, typically, right, he does tutoring for math and science type stuff, so it looks like he's doing a little bit of pressure, looks like at the moment. So, hope you all have a good night, have a good rest of your week. I will see you on Friday for gamey type stuff. And then we'll do more math stuff on Monday, Wednesday. Again, if you have any other questions, show up any other time that I'm on, and I'll be happy to answer it. So, have a nice night, and I'll see you all later. My name's Obi-Wan Pez. This is N Simplex Pachinko. Welcome to the Math Brigade. See y'all later.